Thank you all for joining us today. I think we're ready to start. So welcome, everyone. Thank you for joining us today in this seminar of the European Astrobiology Institute Academy. I want to share with you today a brief summary of the work that you can do when you compare the present-day measurements of different surface platforms and rovers that are exploring Mars with the work you can do in space simulation facilities, in space chambers, and how this can be used to plan the future exploration of Mars, and in particular for the analysis of the sample that will be returned from Mars in the future. So as an introductory frame, I just want to let you know that we're going to be focusing on the present day environment. And this is, of course, very important, mostly to plan the future exploration of Mars, but also to understand where on the surface of Mars there are conditions such that life may thrive, life as we know on Earth. And these are the regions that we call special regions. And also we need to know what is the present day environment in order to design in situ resource utilization methods. Those are the ones that will be used hopefully by astronauts in the future, like the one we are seeing in this artistic impression of Mars. It all started when the international community started to design a deep space exploration strategy. As you know, we have already been to the moon in the past, several decades ago, but there's now an increasing interest in exploring the moon and demonstrating procedures to extract resources on the moon, and also to have humans, that is astronauts, exploring the moon for a prolonged time. Now, this is just the middle point of a long journey, a journey that will take us hopefully to Mars in the decade of the 40s. And in order to make sure that that exploration target can be met, then we need first to demonstrate that we can also bring something back from Mars. And this something that we are first going to bring are the samples of the Mars Sample Return Program. So this is a very ambitious program, but it has been designed with time, and it has been kind of agreed as a global roadmap by 50 countries and 14 space agencies. And as you know, we are already seeing the first steps of this deep space exploration plan. When we talk about Mars, Mars has been explored by different nations and space agencies already for the last decades. And as you can see in this schematic representation, there are different spacecrafts that have been orbiting Mars and are getting information from remote sensing instruments. But there are also a few platforms and rovers that manage to land on the surface. And many of them are right now, as we speak, they are operating and acquiring information of the present-day environment. Most of these missions are focused on investigating the past history of the planet, understanding the geology, the minerals, and interpreting how Mars has evolved over time. But a few of the sensors and instruments that are on board these platforms are devoted to monitoring the present-day environment, and that is what I want to talk to you about today. This is one of my favorite instruments. This is a measurement of RAD, the radiation instrument on board Curiosity. And I'm showing this schematic interpretation of the measurements just to show to you how to compare the received dose that you would have on the surface of Mars with the one that we have in our planet. So if you look at this graph from left to right, on the left side, you have the annual cosmic radiation that we receive within our planet at sea level. And if you compare that with what you would receive on the surface of Mars, that is the red column on the right, you see that there are many orders of magnitude of difference. And this is basically telling you that it's a very harsh environment for humans, but not only for humans, but also for electronics and many other components that we usually use in our life on Earth. Now, this radiation is also harmful for the preservation of biomolecules. So in the case that there was life on Mars, and if that life has been preserved, after being bombarded for many millions of years, bombarded by this kind of high energetic particles, these biomolecules will most probably be very degraded. I also want to take this opportunity to encourage you to go to the archives where the data of all these missions are stored. And in particular, there are two open data archives, the Planetary Data System and the Planetary Science Archive by NASA and ESA. And you can have access to the data from these past missions, not only to Mars, but also to other exploration targets in the solar system. And even missions that are currently operating, including Perseverance or Curiosity, are regularly uploading their data here. One of the measurements that we are most concerned about when we talk about habitability and astrobiology are the measurements related to water. I want to take here this example of measurements acquired by REMS at Gale Crater, that is near the equator. And these measurements were taken about 11 years ago. So we're so lucky that we have different environmental stations working for a long time on the surface of Mars and sending the data back to Earth. And this is an example of just one day on Mars. And as you can see, we have about 24 hours on Mars, just like we have on Earth. And I'm going to guide you through the interpretation of these graphs. Let's follow, for instance, the red line above the TG that represents the ground temperature. And as you can see, as the day passes and the night is falling, the temperatures are dropping below 200 degrees Kelvin. And then with sunrise, the temperatures are increasing above the 0 degrees Celsius. Within one only day, at the surface of the planet in an equatorial region, you're going to have temperature changes that are bigger than 90 degrees. That is really, really big. Now, associated with these huge thermal changes, there are also very important changes in the relative humidity of the atmosphere and of the surface. And the graph that represents that is the blue lines. And as you can see, when the night is falling and the temperatures are dropping, the relative humidity is increasing. In general, if you happen to have a relative humidity that reaches 100, that is what on Earth we define by definition is the saturation. If that happens in the air, you're going to have fogs or you're going to have clouds. If that happens on the surface, then you're going to have frost or you're going to have dew. And the question is, if this is the diurnal cycle of water on the surface of Mars, are there conditions that can allow to form frost or to have dew, or to have something intermediate, which is called brines. And I will talk to you about that later on. So coming back to the temperature is extremely, extremely important for life because all the microorganisms that we know on Earth have a limiting temperature below which they cannot replicate and below which they cannot do any metabolic activity. So if we took one single organism from Earth, an extremophile that is able to tolerate very arid conditions and high radiation doses, there would only be certain windows of time when the temperature is high enough that these microorganisms can reproduce. The graph on the left is showing actual measurements provided by REMS at Gale Crater. The red line, or the red dots, represent the highest temperature measured every day, and the blue one represents the lowest one. So all the temperatures within one day are oscillating within that temperature range. Now, what happens is that if you go underneath the surface, you can model, you can make a prediction of the temperatures, how they're going to look like. And this diurnal thermal change is decreasing as you go deeper and deeper. This is what is represented on the right side. And in particular, for the conditions of the regolith at Gale Crater, you can predict what is going to be the temperature within 15 centimeters or 20 centimeters. And this is what is here represented with the dots and the gray line. And this graph is telling you that as soon as you go beneath the surface, the temperatures are so low that you're always below the temperature limit for metabolic activity and well beyond the temperature limit for replication. So from the point of view of temperature, and based on the limits of life as we know on Earth, only the regions above very close to the surface are the ones that eventually every day have a few hours where the temperature is high enough that they can replicate. And this is, of course, very important for life, as we know. And it's also very important for something that we call planetary protection that I will talk to you about later on. So as we have seen, the temperatures are changing very much within one day. And when those temperatures change, then the water is also changing in the relative humidity of the atmosphere. And this has taken us to make this kind of simplified picture of the water cycle on Mars. We know that liquid water cannot be stable, but it's under our understanding that when the temperatures drop, then the atmosphere and the surface may get saturated, and that will produce frost. But also, while that happens, the water in the atmosphere is being captured in the regolith in a way that I will show to you experimentally later on. And it's also being captured by some salts that have been found on Mars. And these salts can have the possibility to become hydrated, and some of them can even do deliquescence. Deliquescence is a process which is illustrated on the image caption above. And what you can see here is an example of perchlorates. Perchlorates can absorb water from the atmosphere, and then they can melt into something that is liquid and transparent, and it's a brine. And a brine is simply a very saturated liquid phase, where you have a mixture of salts and water. If you mix this kind of salts with the regolith, then you would see something similar, but instead it looks like a muddy mixture. So in our understanding, this is happening planet-wide on Mars every day and every night. And when the temperatures increase, then the water that has been captured is released back to the atmosphere. Eventually, when the water goes up to higher layers and the temperatures are again very low, again, you can have saturation, and this may lead to the formation of clouds. So in a way, it is similar to the water cycle on Earth, with the exception that we don't have this perennial liquid phase or stability of pure liquid water on the surface. So when did we start talking about the relevance of salts on Mars? This happened already during the mission, when the mission Phoenix was operative in the polar region. You may remember that this mission that looked like this artistic impression that is here included, it's a huge lander with solar panels, and one of the purposes of this mission was to investigate the soil, the top centimeters of the soil. So there was this tool that could actually dig into the upper centimeters, and when this was done, we could see some bright patches of water ice. And if this water ice was pure, then it would have immediately sublimated, but instead it stayed for many days. And this made the scientists in the team think that the ice is not pure and is instead mixed with some salts. And the salts are the ones that are giving this frozen mixture higher stability against sublimation. Additionally, by serendipity, I would say, there was an image that was taken of the legs of the lander. And in the image, we could see over different days how some blobs appeared, and the blobs, these spheroids, merged, and they were changing in color or in opacity. So it was there was an hypothesis done postulating that it could have been that some of the perchlorates that were found in the analysis of the soil have actually managed to be attached to the legs of the platform, and they were absorbing water and the liquescing and then freezing. So in order to fully interpret this, we did an experiment at CAP, at the Planetary Simulation Chamber PASC. And in this experiment, we put the salts that had been found on Mars, and we simulated a diurnal cycle similar to the one that is seen in the polar regions, where there is a lot of water in the atmosphere. And we could see how small spheroids of liquid brines were appearing, and depending on the temperatures, we could have frozen brines or we could have semi-liquid brines. And this can be seen indirectly if you use, for instance, infrared spectrometry. You can see the changes between liquid and ice phases. Now, this has been investigated more in depth as we started planning the mission of ExoMars to Oxyaplanum. And in order to investigate this, a specific chamber with control of the relative humidity in the full chamber was designed. What I'm showing here to you is a similar example, but here for Oxyaplanum, we are injecting water vapor, and I want you first just to focus on what happens in the table. What happens is that when the chamber is saturated, what you're first going to see is frost. But eventually, as the temperature changes, then the frost is going to have a transition into dew. So for a few hours, you're going to have pure water, like droplets, that are going to be evaporating very rapidly until they disappear. And this happens to be very interesting for life, because we know on Earth, if you go to some desertic regions, there are microorganisms that can survive with only a few hours of dew. Now, of course, on Mars, you're going to have all the stressors. In addition to having only a few hours of water, you're going to have high levels of ultraviolet radiation. You're going to have many other chemical stressors. And in addition to that, also the high energetic particles that are coming from space radiation. But at least from the point of view, of water, you know that if you have saturation, you eventually may have dew formation. Now, in addition to that kind of cycle of water, pure water, you can also have the interaction that I've talked to you about before. What happens if I put some beakers in the chamber and I include the salts that had been found on Mars, namely calcium chloride, iron sulfate, magnesium perchlorate, or sodium perchlorate. These are just a few examples of the salts that are mixed within the regolith. I can have them in pure form, or I can have them mixed with regolith. And then I just apply the simulation of one full day on Mars, where you have this water cycle. If you just do this within a few hours, you're going to see what I told to you about before. This is the liquescence process that leads to the formation of very saturated brines. And in some cases, you're going to have hydrates. When you have about 10% of salts mixed with regolith, we don't see, with our bare eyes, we don't see the formation of mud, we don't see the formation of liquid, but instead we see some changes in the cohesivity of the products, you see some granularity, and we can measure afterwards how much water has been captured here. So why did we do these experiments? Well, again, the experiments were done because looking at the measurements from REMS, that I told you it has been operating for about 11 years, we had seen that the water volume in the atmosphere near the surface was changing every day. If I take a graph of the measurements of the first more than 1,500 sols on Mars, if I look at the measurement of the volume mixing ratio at about 9 in the evening, and I measure again later on, and another hour later on, and on so forth, until we get to 4 in the morning, what I see is that the volume mixing ratio is always decreasing. And why is this happening? Because the soil is working as a sink, is absorbing water from the atmosphere. And I'm not including here what happens afterwards. When the temperature increases with sunrise, this water is released to the atmosphere. So this is an example where actual measurements from the surface can be used in combination with experiments in chamber to interpret what is happening on Mars. And from the experiments that I've shown before, what you can do then is to take your beakers with pure salts, or the ones where you have combination of salts with soil, and measure before and after how much water did I absorb. And all these experiments are showing that these mixtures can absorb about 50% or 20% in some cases of their weight in water vapor. Basically, this could tell you that if you had a microbe surviving in this soil where there are salts, and if these microbes could tolerate the salts, they would have a daily input of about 1 gram, half a gram of water to do their metabolic activity. So all these experiments have been done within a small chamber, and there are many limitations to what you can do inside a chamber on Earth. The ideal way to explore this would be to have an experiment running on Mars, and this was the purpose of the HABIT instrument. Now, HABIT is an instrument that was designed to monitor the near-surface environment, but in particular, it also includes a small experiment that it's called BOTTLE. HABIT, as you see it here, has a set of ultraviolet sensors that monitor the radiation that you receive on the surface of Mars in the ultraviolet range. It also has a ground temperature sensor to monitor the actual temperature of the surface. And it also has air temperature sensors to monitor the temperature around the surface platform. But what I'm going to focus on is on the brine observation transition to liquid experiment. And this is a small container here, bottle. And bottle was designed to have the salts that we have been investigating. Every container in bottle has a different kind of salt. And within each container, there are 3 electrodes. They are golden electrodes. And what they do is that when the salts get hydrated, like here, when they capture the water, they work as a sink for the water in the atmosphere. They can melt into liquid. This would be full deliquescence, or they can become hydrated. And what you see then is that by measuring the electric conductivity from here to there, you can indirectly interpret how much water has been absorbed. And these are the kind of experiments that you have to run whenever you are designing an instrument that is going to operate on Mars. You have to design it first so that it works on the bench, but eventually you have to do a demonstration under real conditions. Since for this experiment, it was so important to monitor the water cycle, this chamber had to be designed specifically to simulate the water cycle on the surface of Mars at Oxyaplanum. And in the experiments, we were monitoring the relative humidity during one day and the temperatures. And what you would have are the measurements that are obtained on the right. They're not very important to be interpreted in detail, but I just want you to look at the order of magnitude of the electric conductivity. And in particular, once you start having absorption of water or deliquescence, what you have is a huge increment in the electric conductivity. So this could be an indication that there is water is being captured from the atmosphere. Why is this experiment so important? Well, first, because it could be a real in situ demonstration of a diurnal cycle of water that has been hypothesized, but we don't have a direct way of measuring how much water is being absorbed by the soil. But it's also very important because this could be a demonstration of a way to capture water for the future exploration of Mars by astronauts. When we talk about exploring Mars and when we talk about the critical conditions for life, I've told you before, we are concerned about temperatures and then about radiation and then about water availability. This is a large scale map of Mars. And here there are different regions that have been marked depending on the availability of water. Based on the current knowledge of remote sensing observations from orbiters, we know that there are polar regions where ice is stable as a pure water or mixed with salts. We can also have other regions where water is mixed in the regolith and it's stable up to the topmost 5 meters. And we know it because we see when there are impacts, recent impacts, they expose the ice, and ice is sublimating slowly over time. Where most of the missions are landing, that is at these latitudes, we don't have direct proofs of existence of water ice. What we have are indirect evidences of a local cycle of water. Now, if the experiments that we have just seen represent what happens at a smaller scale on Mars, what may be happening, but it cannot be seen from orbit with the satellites, is that whenever you have a mixture of regolith and salts, they're going to be transforming into this kind of briny mud and eventually releasing the water back to the atmosphere. So the access of water can actually happen everywhere on the surface of Mars. And we need to take this into account when we talk about protecting the planet from terrestrial contamination. So this brings the topic to the concern of the Planetary Protection Panel from COSPAR. The purpose of this panel is to design and update the policies that are applied when we explore other environments in the solar system, in order to make sure that we maintain the biospheres of different environments apart. In particular, here you have an example of 2 arid environments. The one on the left is my favorite environment, is Mars, that is Gale Crater. And then the one on the right, that is an image of the Atacama Desert. And we know that there is life within the soil of the Atacama Desert. So we want to make sure that we don't bring that kind of life to Gale, at least while we are exploring if life ever existed on Mars. And this is the idea behind planetary protection. We know life exists almost everywhere on Earth. We know that even the human body, which consists of 10 to the 13 cells, has about 10 to the 14 or 15 microbes living with us. And when we are sending spacecrafts to another planet, in particular to Mars, we are bringing these organisms always within the spacecraft. So we want to make sure that we create a barrier and we don't let these organisms get to Mars and eventually have the conditions to reproduce. It wouldn't be too harmful if you only have one of these microbes being sent there, because eventually it's going to be sterilized by radiation. But if you don't take care of this, and if you're bringing too much bioburden, then eventually one of these cells may find the conditions that are necessary for the cells to reproduce, and you may be contaminating the environment. And that is the purpose then of planetary protection, to make sure that we have measurements in place to produce this barrier that separates both biospheres. The other concept where the present day environment is very important, it's in situ resource utilization, especially if we are planning to design a mission in the future with humans. We need first to test these technologies. Why is this important? Well, if you have the ability to transform resources in space, this is going to decrease the cost of the mission. This is going to increase the capacity of your payload, and it will also reduce the risk for the mission overall and then for the crew. And most importantly, it will also allow to have an extended duration of your mission. So what kind of processes are we talking about? One of it, it's very well known to all of us, just simple classical solar panels. They can produce energy in situ. But there are other ways to produce energy. One of them is the one we need for propulsion. We need propellants that can actually start the launch of a rocket. And the propellants are very heavy. You cannot bring them from Earth. Among them, we need to produce oxygen and methane and hydrogen in huge amounts in liquid state, so that we can bring 4 astronauts at a minimum back from Mars to Earth. We also need to have better knowledge of life support systems. Some of them are being now designed for the International Space Station, but also now there's some research about life support systems for the Moon. We need to investigate about radiation shielding materials, and then we need to have products that can be used for construction. So I'm going to just give 4 examples of in situ resource utilization technologies that take into account the present day environment of Mars. The first one, you have already seen it. We have seen that the salts and the regolith can actually capture water. So in principle, you could have the regolith and heat it and extract the water that has been absorbed during the night. The other application of regolith is to produce construction blocks. You can use it for 3D printing, or you can use it with binders to produce very solid blocks with different forms. And these materials are going to be very good absorbers for space radiation. Right now, as we speak, there is a beautiful instrument called Moxie that is operating within Perseverance rover. And Moxie is a technology demonstrator. That means that it's producing something useful, but in small amounts. In the future, if this works, then it can be scaled up. And what the Moxie is doing is that it is producing oxygen by absorbing CO2 from the atmosphere and breaking it up into oxygen and then carbon. The best way to demonstrate that something is ready for its future sustained exploitation is to have it working at small scale in a mission. And that is why Perseverance included among the payloads Moxie. On the other side, ExoMars, as it was designed before, it included the Habit instrument within the surface platform, and Habit was going to do the demonstration of the water extraction capabilities of salts. This could be a way to absorb water from the atmosphere and have a few grams of water every day in this small container. Regarding the future exploration of Mars and the Mars Sample Return Program, what does the present day environment tell us about this? Well, this is a beautiful GIF, an animated image, a selfie of Perseverance rover. And I don't know if you're familiarized with this mission. I think we're going to have another talk within the EAI Academy about the Mars Sample Return Program. But what you're looking at here is a rock that has been drilled by the rover, and the rock tubes have been sealed and are now within the rover. The plan is to collect about 30 tubes, and in the future, there's going to be a lander that will get to Jezero. And the nominal plan is that the rover will go to this lander, will deliver the tubes, and they will be launched within a rocket back to this platform. And this orbiter will bring the samples back to Earth. And this full architecture will be true. It will bring, in 10 years from now, will bring a collection of samples back to our labs. What does the present environment tell us about the state of these samples? Well, I would like you to go to the PDS, the Planetary Data System, and look into the first initial reports that document, I think, the 14 first samples that have been acquired. Every sample is sealed within a tube that looks like this, for comparison with the size of your hands. This is an example of the borehole, an image taken with Watson, and this is the way the rock looks within the tube just before being sealed. As you can see, the tubes are always going to have some space above, where what we're going to have is atmosphere from Mars. And the amount of molecules that we have within will depend on the pressure and the temperature at the moment of sealing. And of course, as the samples stay on Mars, the rocks and the atmosphere are going to be stabilized over at least 10 years. This is an example of the instrument, the observations of SuperCam in the infrared, as they were acquired on the abraded patch of one of the samples. This is an outcrop where one of the samples was acquired, and infrared measurements tell you that by monitoring different days at this rock, we can see an increased signal of water. As the days passed, the sulfates that are within this rock were absorbing water. So this is indeed a demonstration. There is a diurnal interaction or seasonal interaction between the surface of Mars and the water in the atmosphere. Finally, once these rocks are safe within their sealed tubes, the tubes are going to be included in this capsule, and they're going to be brought back to Earth. And the most important part of this capsule is that it has to protect the samples from overheating. So this is a heat shield, and eventually the samples are going to cross the atmosphere of the Earth and land, and then they will be brought to a laboratory where they will be opened. And of course, once we open them, we will have air encapsulated here at Martian pressures, and we would need to make sure that the atmosphere of Mars is extracted and analyzed in the convenient conditions such that there is no cross-contamination from Earth. So this could be a summary of the present-day conditions, the present-day environment of Mars, and what we can learn using space chambers. So if you have any questions, I'm happy to answer them. Thank you.